students, welcome back to the channel. So we know that your midterm exams are coming, and to help you with your preparation we have started this series, and today's video is going to be super important because we are going to cover the entire solutions chapter in just one shot. So whether you have studied everything or not started at all, this video will cater all your needs. You can revise if you have already studied, and you can also understand the concepts. So please grab your notebook and pen and note down all the important things, and let's get ready for the midterm examination. So what all topics we have in today's class? So if you see, we have 7 topics. Okay, first is the types of solutions, then I have concentration terms, solubility, vapor pressure, ideal and non-ideal solutions, colligative properties, and abnormal molar mass. Now coming to types of solutions. So okay, before that I want to discuss the blueprint, or how many types of questions are being asked from this solutions chapter. So this blueprint is according to 2025 paper, okay, means 2024-2025. The new blueprint is not out, so whatever is the previous one we are following that. So according to this there will be total 13 marks from this chapter, okay, and if I distribute this 13 marks, there will be 2 questions of 1 marker, that is MCQ or FIB type, fill in the blanks or MCQs. Next 2 questions, 2 marker you will get 1 question, okay, 3 marker you will get 1 question, the theory question, and there will be 3 marker 2 questions of numerical type, okay. So total if you see here I am getting 6 marks, 3 marks, 2 marks and 2 marks. So total it is 13 marks, okay. So be ready, you will get 1 2 marker theory question, 1 3 marker theory question, and 2 3 marker numericals, and 2 MCQs, okay. This is clear. Now let's move to the topics. First is the solution and its type. So very simple, based on the physical state of the solvent, solutions can be of 3 types: solid solution, liquid solution, and gaseous solution. So I'll show you the example. This table is there in the NCERT book. You have to remember, what you have to remember, these examples. Where can it be asked? It can be asked in the MCQ question. So for example, they will give you which of the following is an example gas and solid solution. So here you can see that if I have all the gas solvent, I call it gaseous solution. If I have liquid solvent, we call it liquid solution. Solid solvent, solid solution. These examples, please go through it thoroughly. For example, it is given amalgam is a amalgam of mercury with sodium. What is the solute here? What is the solvent here? So we know liquid is the solid and solid is the solvent, okay. So these are examples, so please remember and just overlook these examples from your book. Now coming to concentration terms. So we have 7 concentration terms, and out of that these 3 are very important. So first concentration term is mass by percentage, volume by percentage, mass by volume percentage, parts per million, mole fraction, molarity, and molality. Now if I tell you what is mass percentage, the formula is mass of the component divided by the total mass of the solution into 100. So students, since it is a revision video, I am going a bit faster. You can pause the video and note down the formulas, okay. So it is what? Mass of the component by divided by the total mass of the solution into 100. Then I have volume. So here is an example. If I give you 10 gram or 10% of glucose, that means 10 gram is glucose and 90 gram is water, okay. Now coming to the next thing, that is volume percentage of the component or volume percentage. So volume of the component in the solution divided by total volume of the solution into 100. Now here also I can give a similar example. If I have 10% ethanol, volume by volume, so that means 10 ml ethanol will be in that concentration of 100 ml, okay. In the concentration of 100 ml, 10 ml is what? 10 ml is ethanol and 90 ml is water, right. So next we will discuss is mass by volume percentage, or W by V. This means what? You have percentage of the component, mass of the component in the solution divided by the total volume of the solution. So for example, if I write here 10%, okay, W by V ethanol, okay, that means in 100 gram of solution, okay, in 100 gram of solution there is 10 ml of ethanol, okay, clear. So next, moving to parts per million. So number of parts of the component divided by the total parts into 10 to the power of 6. We'll go to the next one. So here also I've given you an example. A liter of seawater contains 6 into 10 to the power of minus 3 gram of dissolved oxygen. Such a small concentration is represented in the parts per million. But the main thing that we are going to discuss is mole fraction. This will be used again and again. Mole fraction is the number of moles of the component divided by the total number of moles of all the components. So if I have an example here, if there is a binary mixture A and B, okay, so mole fraction of A, mole fraction of A will be number of moles of A divided by number of moles of A plus number of moles of B. Okay, moving to the next one just a minute, I will be adding two more things here, molarity and molality. Okay, so what is molarity? Molarity formula, how do we represent molarity? With M, capital M, and molarity is equal to number of moles of solute by volume of the solution in ml. Okay, volume of solution in ml into 1000. Okay, now if I write 2 molar, what does it indicate? It indicates 2 moles of solute, 2 moles of solute in 1 liter of solution. Okay, now similarly we have molality also. Okay, molality is denoted with small m. Okay, now what is its formula? So molality is equal to number of moles of solute by mass of the solvent by mass of solvent, okay, in kg into 1000. Okay, so now if I have 2 molar, okay, 2m, so what it will be? It will be 2 moles of solute, okay, in 1 kg of solvent. Okay, that is the definition. So please note down these two formula, pause it and note down. Now moving to the next concept is solubility. Now solubility is of 2 types, solubility of solid in liquid and solubility of solubility of gas in liquid. Now when I talk about solubility of solid in liquid, so what are the factors affecting here? Nature of the substance. So here you should know that like dissolves like, that means polar solute will be dissolved in polar solvents, non-polar solute will dissolve in non-polar solvents. Next we have temperature. So solution or this dissolution process can be both endothermic and exothermic. So if it is endothermic, if you if you increase the temperature, solubility will increase. If it is exothermic, if you decrease the temperature, solubility will decrease. Now coming to the next one, that is pressure, and pressure has no effect in the solubility of solid in liquid. Next topic is what? Solubility of gas in liquid. So here also we have 2 factors, pressure and temperature. So if you increase the pressure, solubility will increase, and if you decrease the temperature or if you decrease, the solubility decreases with the increasing temperature. Okay, moving forward, so you can easily guess this, right? So if you have some gas dissolved in liquid, if you heat that, if the temperature increases, you know the gaseous particles have very high kinetic energy, right? So what will happen? They will escape and the solubility decreases. Okay, so here this solubility, to explain the solubility of explain the effect of pressure on the solubility of gas in liquid, there is a law, that is Henry's law. Okay, so Henry's law states that is a gas law which states that at the amount of gas that is dissolved in a liquid is directly proportional to the partial pressure of the gas above the liquid when the temperature is kept constant. Okay, so that means what? If you see, if I have a gas like this, if there is a liquid here and there is some gas here, okay, so the solubility of this gas in the liquid depends on the partial pressure of the gas. So how much gas is present, that much it will be soluble. So how can I write the formula? P of the gas is equal to KH into X of the gas. Okay, so KH is Henry's constant, X gas is mole fraction, and P of the gas is the partial pressure of the gas. Now there is some application of Henry's law. So here I can explain you with more easily with the diagram. You can see, suppose this is the liquid, okay, and here these gaseous particles are there. So if you increase the pressure on the gas, the solubility of the gas will increase. That is what is called as Henry's law. Next we have applications of Henry's law. So it is widely used in the soda bottles. Okay, so to increase the solubility of the carbon dioxide gas in this beverages, the carbon dioxide, these gases are sealed under high pressure. Next we have scuba divers. So scuba divers, what happens in the so when scuba divers go down deep into the ocean, the pressure increases, the solubility of the gas increases. Okay, so there's one particular gas, that is nitrogen, which gets dissolved more. Now when this scuba diver comes to the surface, what happens? Since the pressure is decreasing, solubility will decrease, so the nitrogen gas solubility decreases, and the nitrogen comes out of the body of the blood in the forms of the bubbles, and these bubbles can block your arteries and veins and can cause severe pain. That medical condition is called as bends. So to prevent this, what happens? In the scuba diver's oxygen tank, helium gas is mixed. Why? Because helium gas is having low solubility. Okay, now here from Henry's law I have one important conclusion also. So if you see, KH is proportional to mole fraction of the gas, or KH is inversely proportional to solubility, right? So helium gas KH value is very high, so its solubility will be less. Now coming to the next thing, that is applications of Henry's law in mountains. Okay, so what happens when, if you imagine a mountain, okay, so when a climber or a mountain climber goes to the top, there is less atmospheric pressure. If pressure is less, solubility of the gas will be less, so oxygen is less soluble in the blood at higher altitude, so our brain does not get enough amount of oxygen, as a result of which there is a medical condition formed called as anoxia. Okay, this means what? When an anoxia happens, person is not able to think properly, its nervous system is not working properly, such type of symptoms are found. Okay, now with applications of Henry's law, we'll go to the effect of temperature. So we have just seen that when temperature increases, what happens? KH value increases. Okay, now if KH value is inversely proportional to solubility, so if KH value will increase, solubility will decrease. So indirectly I can say that if temperature increases, solubility decreases. Okay, now we will move to a new concept, that is vapor pressure. So vapor pressure is what? First let us understand. Whenever you have a closed container and you have some liquids in that, okay, so the liquid will evaporate. So at the same time the liquid cannot escape out, the vapors cannot escape out because the container is closed. So what will happen? The vapors will hit the container and then again will condense. So there is a two process happening here, evaporation and condensation, right? So when the rate of evaporation and the rate of condensation is equal, in these cases we call it as rate of evaporation and rate of condensation. If it is equal, then we call at that point that equilibrium is reached. Okay, we call that at that point of time equilibrium is reached. Now once this equilibrium is reached, that means what? Whatever vapor is present here at this equilibrium, that vapor exerts some pressure on this liquid, and that pressure is called as vapor pressure. Let me repeat it once again. The first condition is the container should be closed. There is evaporation happening, there is condensation happening. When the rate of evaporation and rate of condensation is equal, that time we get equilibrium is attained, and at this point of time when the equilibrium is attained, the pressure exerted by these vapors on the liquid surface is called as vapor pressure. Okay, now vapor pressure we will study. If the solution is a liquid solution, what will be the vapor pressure? If it is a liquid solid solution, what will be the vapor pressure? Okay, so that we will discuss in the next section. Vapor pressure in liquid, vapor pressure in liquid solution. So here comes a new law, that is Raoult's law. So Raoult's law say that for a solution of volatile liquids, vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. So for example, if you see, you have two components, okay, one green component and one pink component. Okay, so green will evaporate, pink one will also evaporate. So green will create some vapor, pink will also create some vapor. So I can say that the pressure of created by A will be proportional to mole fraction of A, and the pressure created by B will be the mole proportional to mole fraction of B. XA and XB what? Mole fraction in the solution. Okay, mole fraction in solution. Okay, in this the pressure created PA is proportional to XA and PB is proportional to XB. Now to remove this proportionality, what we can do? We can multiply a constant, that is P naught A. Now what is P naught A or P naught B? It is the pure pressure of pure A. And what is P naught B? Pressure of pure B. Okay, clear? Means when there is no A or when there is no B present, whatever pressure is created, that is P naught A. When there is no A present, whatever pressure is created, that is P naught B. Now what happens? What is the total pressure then? If you see at this point of time in this container, what is the total pressure? Total pressure is PA plus PB. This total pressure is PA plus PB, that is given by Dalton's law. So what I am saying here is, see, if you have a container, you have two particles A and B. PA is the pressure here, PB is the pressure here. Then what is P total? P total is equal to PA plus PB. This is Dalton's law. Okay. Now, but what is PA equal to? PA is equal to P naught A XA and PB is equal to P naught B XB. Okay. So this is Raoult's law. This is Raoult's law. You are getting the difference? How can we define this PA? That comes from the Raoult's law. Okay. Next, we'll discuss the graph for this one. So you can see this is the graph of a ideal solution. You have a mole fraction of x1. So this goes here, and this is the total pressure. So when x1 is equal to 1 means there is no 2 present. The pressure is P naught 1, and when there is only 2 present, no 1 present, the pressure is P naught 2. Now here you can join a line that is equal to P1 plus P2. Clear? Moving forward, we have mole fraction in the vapor phase also. So when they have evaporated, there will be vapors of YA created, vapors of B created. Its mole fraction can also be calculated. So we have YA is the mole fraction of A in the vapor phase, YB is the mole fraction of B in the vapor phase. So what is YA? Mole fraction of A in vapor phase. Okay. Moving forward, we have vapor pressure in solid liquid solution. So in solid liquid solution, what will happen? See, when the vapor is created, when all the particles are pure solvent, these all were evaporating. Now when you added a solid solute, okay, solid solute will not evaporate. So what it will do? It will block, means you can see now 1, 2, 3, 4, 5, 6, 7 particles were evaporating. Now only 4 particles are evaporating because solid are non-volatile solutes. So in that case, what will happen? The vapor pressure decreases. So that is why whenever you add a solid to a liquid solution, the vapor pressure will decrease. Okay. Next, we have graphene formula for this one. So you can see this is only solute is there. So there is no another component is not there because only one component is creating the vapor, and this is the formula for that. Now moving forward to ideal and non-ideal solutions. So ideal solutions are those which obeys Raoult's law. Non-ideal solutions are those which does not obeys Raoult's law. Okay. So non-ideal solution are again of two types: positive deviation and negative deviation. We will see what is that. So first let's see the difference between ideal and non-ideal solution. This is a very important question. It can be asked definitely in the exam with exam. Like you must remember the definitions, the differences and the examples of both of them. So it obeys Raoult's law, does not obey Raoult's law. Delta H mix 0 not equal to 0, V mix equal to 0 not equal to 0, AB interactions equal to AA BB interactions, AB interactions not equal to AA BB interactions. Now I told you non-ideal solutions can be of again two types: positive deviation and negative deviation. So when I say, see, when I say here it does not, one second. Yeah, it does not obey Raoult's law. That means what? P total is not equal to PA plus PB. Okay. So if it is not equal, P total can be more than PA plus PB. Okay. Or P total can be less than PA plus PB. So if it is more than, it is positive deviation. If it is less than, it is negative deviation. Okay. So you can see here. Yeah. So okay, positive deviation, you can see P total is more than P1 x1 plus P2 x2, and here P total is less than P1 x1 plus P2 x2. Here AB interactions are weaker than AA BB interactions. Here AB interactions are stronger than AA BB interactions. Next you can see example: ethanol plus acetone, CS2 plus acetone, phenol plus aniline, chloroform and acetone. These are the examples. Okay. delta H mix is greater than 0, delta H mix is less than 0. You can add one more point about V mix. Delta V mix is greater than 0 here and delta B mix is less than 0 here. Okay, so please, this is also a very potential question. Definitely it can be asked in 3 marker or 2 marker. Please remember these examples, differences, and do practice writing this one. Okay, now we will go to the graph for this one. In positive deviation there will be curve towards the top, in negative deviation there will be curve towards the down. Okay, so this also can be asked in the exam, so you have to draw this diagram and prepare. Next we'll talk about azeotropes. So what is azeotropes? Azeotropes are some binary mixtures, okay, which have the same composition in the liquid and the vapor phase, and they boil at the same temperature. Okay, azeotrope again can be of 2 types, maximum boiling azeotrope and minimum boiling azeotrope. So if you see, you have to learn their differences also. Maximum boiling will show negative deviation, minimum boiling will show positive deviation, and you can see the examples as well here. Okay, then we will go to the next important topic, that is colligative properties. So what is colligative properties? These are those properties which depend on the amount of solute added irrespective of the nature of the solute added. Okay, it depends on the number of solute particles added. So there are 4 colligative properties. You have to know their formula. First one is relative lowering of vapor pressure. So whenever you add a solute, the vapor pressure decreases. And what is the formula? Delta P by P naught. Okay, the P naught minus P. So what is P naught here? P naught is the pressure of pure solvent. Pressure of pure solvent. Okay, P is what? Pressure of solution. Okay, next you have XB. XB is mole fraction of solute. Mole fraction of solute. Okay, and then here also, in case of dilute solution, this XB can be written as NB by NA. Next colligative property is elevation in boiling point. So whenever you increase, when you add a solute, the boiling point increases. And how do we represent it? The formula delta TB is equal to KB dot M. What is delta TB here? Delta TB is TB minus T naught B. What is TB? Boiling point of solution. What is T naught B? Boiling point of solvent. Okay, KB is the constant and M is what? Molality. Okay, so this is the formula here. Okay, so W2 mass of the solute by molar mass of the solute into 1000 by mass of the solvent. Okay, so I'm just writing W1 here. Next we have depression in freezing point, almost same formula, means similar formula, delta TF is equal to KF into M. So whenever you add a solute, the freezing point decreases. Okay, so here it will become delta TF is equal to T naught F minus TF. T naught F is the freezing point of solvent and TF is freezing point of solution. Okay, KF into M, W2 by M2 into W1, where it is the mass of the solvent. Okay, next we have osmotic pressure. Osmotic pressure is important concept here. So now let us first understand what is osmosis. Okay, so if you have a container and you have a semi-permeable membrane, this side you have a solute which is concentrated one, okay, and this side you have a solution which is a diluted one. Semi-permeable membrane means what? It will allow only the solvent particles to pass through it. So here it is dilute, means more solvent particles are there, so they will flow to this side. Okay, this process is called as osmosis. Okay, now if you want to stop this osmosis, what you will do? You will apply some pressure on this side. You will apply this pressure on this side to stop the osmosis. So that pressure which is exactly required to stop osmosis is called as osmotic pressure. And how do we denote it? With pi. And the formula for that is C into R into T. Okay, C is here molarity. C is molarity. In other all concepts we have used molality, but here it is molarity. R is what? R is gas constant, 0.083 liter ATM mole inverse Kelvin inverse. Okay, and T is temperature and it should be always in Kelvin. Okay, next we have was something called as isotonic solution. So if two solutions have equal osmotic pressure, then we call it as isotonic solution. Now we have another concept of reverse osmosis. Now see, if you exactly apply pressure equal to the osmotic pressure, then osmosis will stop. But what will happen, for example, osmotic pressure is 10 Pascal. What will happen if you apply 50 Pascal? So you are applying 50 Pascal pressure on this side. So what will happen, the solvent particles from this side will start flowing in this direction. Reverse osmosis will happen, and that is something we use as RO, purified water. You might have heard in different ads of filters and all. So RO stands for reverse osmosis, and it is used, a very, very important phenomenon which is used in the desalination of water. Okay, so you can see the direction of the osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through the semi-permeable membrane, and this phenomenon is called as reverse osmosis. Okay. So yes, next students, this abnormal molar mass is might be deleted, or it is there, because in NCERT book this part is not there, but in questions it might be asked. So let us just discuss it quickly. So sometimes what happen, let me give an example, a solute NaCl. Okay, you have added one molecule of NaCl, but when it goes into the solution, it dissociates to form Na plus and Cl minus, and you know colligative properties depends on the number of particles added. So you have added now 2 particles actually, but you think that you have added 1 particle. So there is an abnormality here, right? So this can cause a problem in the calculation of molar mass. So that molar mass which is calculated in this way is called as your abnormal molar mass, means which is not the actual value. So now what happens here, this abnormal molar mass can be corrected by using a factor called as Van 't Hoff factor. So here we have I is equal to normal molar mass by abnormal molar mass, or absorbed colligative properties by calculated, or number of particles before after dissociation by number of particles before dissociation. I'll give you some example. For example, NaCl will dissociate to give you 2 particles, so I value is 2, MgCl2 is equal to 3, Na2SO4, here also we will get 3 because 2 Na plus ion and 1 SO4, 2 minus ions. Okay, so now sometimes what happens, the association and dissociation is not 100%. In that case, we have this formula to calculate the Van 't Hoff factor. So alpha is equal to I minus 1 by n minus 1, where alpha is degree of association or dissociation. Okay, and we have I Van 't Hoff factor, n is the number of particles. Clear? So this is the all concept from the chapter solutions. I think I have covered it within 30 minutes, so you can revise the entire chapter in 30 minutes, and do not worry, my next video will be coming where we are going to solve all 1 marker questions from this chapter, and the next video will be coming on all 2 and 3 marker questions. So if you just follow these 3 videos, the entire solutions chapter will be done, and I will be preparing like this small and short video so that you can do a quick revision. So that's all in this video, my dear children. Thank you so much and all the best for your midterm. If you have any doubt, please put down in the comment section. I am going to reply all of them. Okay, thank you so much.